So, um, good afternoon, everyone, or evening, good morning, wherever you are. This is Debosh Live, and today we have a special guest from the community that we're attempting to bring on board to talk, Eric Brombo, and he is going to cover his DS Pod series of boards when he resolves his audio issues. Um, so, in the meantime, we see a new face today. We have uh, Lawrence King of Dragon Board 410C fame. So go ahead and tell the people about yourself and kind of give us the kind of the short version of it, so we can
Hello,
maybe add like
my
a
name's
bio
Lawrence
in the
King.
end.
I've been developing hardware mostly for multiple decades,
Okay.
and a year and a half, or almost 2 years ago, I retired. And in my spare time, I've been working on a little family of boards to make things easier for software developers using the Zephyr operating system. Uh, in the past, I was responsible for the Dragon Board program at Qualcomm, and developed and released the Dragon Board 410C, and had a hand in getting Qualcomm to upstream some of their millions of lines of patches, and they're almost done now. But it's taken a decade.
Only a decade. They're most of the way there.
I wouldn't say they're 100% there, but they're getting there.
Very cool. So yes, it's a pleasure to have you on the show, and it's probably kind of short notice to have anything prepared. I did notice that Fixer shared um, a link about a new project that you're working on. I figure you want to probably talk on the devEco stream proper. I don't know if it's a open hardware project, or if you wanted to open it, if you wanted to contribute it to Devosh, that's definitely welcome. But I'm not going to force your hand on any of this. This is kind of a voluntary, hey, let's hang out and
So
make hardware kind of thing.
I've been looking at the various licenses that are available, and I'm happy for any of the makers to take it and build it and use it, but I don't want commercial companies building it and selling it. So
Okay.
started using a Creative Commons license that allows remix and use, but not commercial.
Okay. So
So that should answer your question about, is it open source or not?
it's mixed source.
Yeah.
Okay. Yeah, I think for our intensive purposes here, we stick to kind of like the mostly open. We're not gonna say that we have free silicon yet. We just want to do board level schematic. We usually present it in the form of KiCad. Hello, did you get through with audio? No.
No.
Oh man. So we might.
So the boards are all built with KiCad.
Okay.
Uh, I hadn't planned on releasing the KiCad files themselves, but I will release the schematics, and you'll
Okay.
be able to buy boards.
Okay. Well, I think
So I don't know if you're going to call that truly open source or not.
no. Yeah, it's kind of like kind of like the Arduino Q, sort of open source.
Yeah.
Yeah, I understand. Um, so I guess while Eric continues to work on his audio issues, we can cover um, the previous projects for Devosh that we've presented in the past live streams. One of them is the robotic arm by Heavy Falcon, and he has a little YouTube video we can play. I think that people would be interested in that. So let me see if I can pull that up. In the meantime, you guys can go ahead and chat if you'd like. I have to find the link. I had it earlier, but find it.
I'll give you a little update on my boards. I actually have put up a website last week at zedboards.com. So that's ZED hyphen BOARDS.com. And it'll give you pretty good descriptions of each board, but there's no link to buy them yet.
Okay.
And these boards are fully compliant with the Zephyr operating system.
Cool.
So
yeah, you do know there is a Z board already, right?
That doesn't have a hyphen, and I don't have a trademark. It's a operating as. So yes, I know there is a Z board,
Yeah.
but it's not really in the same space.
This is iLink's FPGA board.
Yeah.
Yeah.
I selected the name Z because we're Canadian, and the last letter of the alphabet doesn't need to rhyme with the song.
Yeah. So yeah, I'm not sure what's
because I
going
wanted the
on
letter
with
Z.
the lyrics.
I wanted the letter Z because it is part of the Zephyr ecosystem.
Right, right. Yeah, and I kind of figured that out, but yeah, it's confusing. It happens sometimes. When I named a board or a project Pi 5, and then the Pi 5 came out, and it's the same thing, and nobody knows what I'm talking about if I talk about my project, because of course Raspberry Pi 5 is like ubiquitous, so that's kind of interesting. But yeah, it's fun coming up with names that don't clash out in some ecosystem somewhere. Like devash is actually someone's name, I think. It's actually maybe a French name. I don't know. It's a name.
It's a classic Indian name, actually.
Indian. Okay. Well, you knew this. Good. Well, we got to get a guy named Devash to come on for the meta value. So let's go ahead and show Heavy's his robotic arm thing. So I'm going to pop it open another window real quick on my let's see if I can do this. Maybe I can do it on the overlay channel so that we don't have to have another video or another share. Let's see here. Maybe not. Alright, maybe not. Alright, so I'm gonna have to share my whole screen, which is fine. Let's see. Alright, camera 1, camera 2, desktop. It's me. Hello, everybody. Alright, and so this is the Omnibot robotic claw that was presented in the last few episodes. He has a working video, and I'm going to play the video so you can see the progress in the production quality that he rolled into the project. He did a really good job on this.
This is the Omnibot forklift by Hackpack. It's pretty cool, but it doesn't really do much. And this is my fully upgraded Omnibot. It's got a robotic gripper and an FPV-style remote control, straight from your phone. But first, we need to show how we got here. I want to turn this Omnibot into something useful, so I think that swapping it out with another tool would be perfect. This is the robotic gripper I designed, and it replaces the original fork assembly. It uses a continuous servo to rotate this worm drive to open and close the arms. I also added a slow
Okay, does anybody hear me?
things up
Ah,
more
yes.
easily.
Hi, Eric.
Anybody?
So the
Oh,
gripper is
hey,
crispy,
sounds like
but you gotta
I'm here
the
now.
remote
Okay.
could use an upgrade.
So are we ready to do something?
Yeah, I'm showing off Heavy's video for his robotic arm.
Now
Okay.
we have a web
Gripper.
interface for the Omnibot using a Raspberry Pi server. You can access
That might be a little
any
stupid.
device
I
using
started a YouTube
I'm really
window,
happy with that.
and there's nothing there under
Uh-huh.
devosh.
Hey, wait, is Eric working now?
Eric is working
Yes.
now.
Hey, all right, cool guys. Sorry, I just wanted to make sure. Hope you have a great show. I'm watching on Twitch now.
Yeah.
You're watching on
We had
Twitch.
to
Is the
decide-
YouTube not working?
The YouTube's not working. I don't know what happened. It's okay though. Let's just roll with
Okay.
Twitch. It's okay.
Okay.
We'll fix it for next week.
Now we can
Thanks, gentlemen.
Okay, thank you.
Yeah. So that is the culmination of multiple weeks of work on the robotic arm gripper. He made a nice little video. I think it has some nice production value rolled into his video, which is fun. Streaming YouTube through YouTube is like YouTube session, but okay.
This was a really fun project to make.
Yeah.
If you want to build it yourself, a link to the GitHub repo and all the variations is in the description.
Okay.
Thanks for watching.
Yes, and he actually provided a GitHub page, which I started from, which has the 3D files in step format, so you can load them up and modify them, and the video link, bill of materials, wiring diagrams, all the nice stuff, so you can replicate his work. So you don't always have to be like completely open source, open hardware to be open hardware, at least at some level. And the part that's open hardware for this is his hack, which is the 3D assemblies. And so let's go back to our guests and get Eric's. Eric, can you go ahead and share your screen on your side?
Sure.
Okay, thank you. Yeah, I really don't know what happened with the audio earlier. I'm sorry about the hiccups.
Yeah.
Growing pains.
Okay, so I'm trying to click on the. Okay. Are you getting anything?
Let me see. Yeah, I see stream. Let's see if how that looks. Okay, yeah, now you can go ahead and share your web page. Good. Let's make sure this is as big as it can be.
Okay, it takes
All right, go ahead.
a little bit for that to come across. Okay. Okay, I've got my screen shared, and
Okay. All right, before
This
you
is-
before you launch into it, it'd be nice to
Right.
have like a introduction to yourself, and then
Okay.
kind of the rationale for
heck
the
am I?
project. Yeah, who are you?
Right.
And then go
Right.
on and kind of describe what you have there.
Okay. So I'm Eric, Eric Brumbaugh. I've been working in digital signal processing for many, many years. Started out doing a lot of government work in radios and so forth. And then about 20 years ago, I started playing around with synthesizers and got involved in a couple of synthesizer manufacturers of doing digital signal processing and embedded code for primarily Eurorack synthesizer modules. And I have about a dozen products out there that were on the market for a while and were pretty well received. Not doing so much of that anymore. The guys that I was working with have all died or retired.
Oh boy.
So I'm kind of doing a lot of hobby work on my own these days. And I've been following along with all the latest goodies that come out and having an interest in how the latest hardware can be applied to the kind of work that I enjoyed doing. Most of these things that I did were audio oscillators and effects. So that'd be things like, wavetable oscillators and FM synthesis oscillators. And then there's also audio effects like, reverbs and delays and chorus and flangers and all that kind of fun stuff that people like to use to process their sounds so that they sound different.
Yes.
So last year sometime, I was cruising around and I came across the Milk V
Milk 5.
development boards.
Yeah.
If you've seen those, they were making a big noise about 2 years ago, and basically they're a little SoC that's designed for IoT cameras, I guess, for mounting outside your house. And when those things are running, then they have fairly heavy pipeline inside them for image processing, but they also have a stereo audio codec built in, and they have 64 megabytes of DRAM that's inside of a little 56-pin QFN package, and you can get an entire tiny Linux up and running on them, and it'll boot in a couple of seconds, and at that point you can do anything you want with them. And so I started getting interested in how that could be applied to audio processing, and I started thinking about how that would work, and I set that aside for a while because working on getting Linux working is kind of a pain in the ass. I saw some other microcontrollers coming out, like the RP2350 from Raspberry Pi, and I was curious as to how I could do the same thing on those. And after a while, I had a handful of different projects that all seemed to be converging on the same sort of thing, and I decided to put together the DS Pod. And what this is, as I describe it here, is a small ecosystem of audio DSP boards, and I've sort of abstracted all of the common stuff, the user interface, which is a little LCD with an encoder on it so that you can navigate through the different effects that you need. And then it's got some control voltage inputs and audio inputs and audio outputs. And then the kind of processor that you want to run on that is controlled by a little daughter board that plugs into the back of it. And I've got a fair few of different daughter boards in here right now. I've got one for the CV1800B, which is the SoC that's on the Milk V.
Yes. RISC-V.
Yep, Milk 5, I guess. I don't know what it's called. I've never heard anyone say it.
Yeah.
It's got a RISC-V in it, so I guess Milk 5 makes sense.
Yeah.
Then I also have one for the RP2350, and the goal there was that those guys have a nice QSPI interface on them that can handle both flash and PSRAM at the same time, and I wanted to see how that would work.
Yeah.
Then I did one for the ESP32S3, and that one I'm interested in primarily because the Tensilica extensor processor that's in those First of all, it's a dual core, so that's fun, similar to the Raspberry Pi RP2350. But also, it's got some vector extensions in it that would be fun to play around with.
Yes, definitely.
But then another one that came out was the STM32H7R3, and I was curious about those because most of the work that I've done in the past for all the various synthesizer manufacturers that I've done code for, we used STM32s, and we gradually worked our way up from the F4 series parts to the F7 series parts, and then eventually kind of topped out on the H7 because they've got a great big ARM Cortex M7, and they have very high clock rates, 480, 550, 600 megahertz. And I was just curious to see if the 600 megahertz core that they had in the H7R3 would give me any additional capabilities that I couldn't do on the other ones. And so I've built those four, the 1800, the 2350, and the S3 and the H7R3. I got all those up and running, and I did a lot of comparison. I basically have the exact same user interface running on all four of them.
Cool.
The code is very portable from one to the next, and I've got a lot of low-level drivers for the LCD and audio and stuff that is portable from one to the next. So it was very easy to do apples-to-apples comparison of how the library of effects that I have performed on these different processors. And so that's kind of where this went. The goal was just to take the exact same code and try running it on a bunch of different machines and see where the strengths and weaknesses were and what the different features brought to the party.
Okay,
So
that's really cool. Did you end up using a graphics library like LVGL for?
Well, yeah, in as much as I wrote my own library.
Okay.
I looked at LVGL, and the thing about LVGL is that it's very much centered on touch screens.
Yeah.
And if you want to have, buttons and controls that aren't on the screen and accessible through, some sort of a touch interface, then you have to do a whole lot of extra work to bind those into the system. And I just wasn't feeling up to it. But LVGL has a lot of nice features that I would like to have, like the ability to draw nice arcs and fat lines and very friendly looking flat user interfaces. And I would like to explore that in the future, but at the time that I was making the decision on how to do the user interface, LVGL just was putting more roadblocks in my way than I wanted.
Yeah.
So I have my own very stripped down graphics library that does a lot of the things that I need, but there's a few things that I would like it to do that having recent, for instance, how to draw an arbitrary arc. I've looked around at how that works, and it gets complicated really fast.
Yeah.
Lines and circles with Bresenham's algorithms are really easy to do,
Yeah,
but as soon as you
circles.
want to draw arcs, you have to start using all kinds of trig, and I know how to do the trig, but I just have this aversion to doing floating point math and stuff that has to run fast.
Yeah. So you have to transform.
Actually,
it
to
into
draw an arc, you
integer.
only need to do square root. You
Uh-huh.
don't need to do all the rest of the trig.
Yeah.
I wrote a package for Teledon terminals in the 80s.
Uh-huh.
And specifically, I wrote all the code for arcs and circles using Bresenham's.
Right.
Yeah.
Yeah,
I've
so
coded it in
I guess I
assembly
was just
before.
not looking at the right example code, but eventually I might get around to integrating some of that stuff into mine. But so far I've been able to get along without it. Just kind of wished that I had some of those things. Then
So, on a
in
side
the
note,
last,
I brought up LVGL on my boards in the last couple weeks, actually.
cool.
And it has, at least in the Zephyr implementation and in their demo programs, it actually has inputs for a knob like you've got with a push on it, as well as individual switches.
Okay.
So they were already integrated into the samples.
Okay.
Yeah.
Well, I guess I need to go back and look at that again. I have
Yeah.
run it on the ESP32S3, and that's under FreeRTOS, which is the OS that the folks at Espressif ship with their development system.
Yeah.
Yeah.
Or even Expressive is moving over to Zephyr.
Uh-huh.
Yeah.
Yeah, I've heard
Everybody
that.
is.
Everybody is.
Join the party. Jump on the bandwagon.
Yep.
Learn device tree.
All us bare metal folks are left behind.
It's
Um,
not
yeah.
too bad.
Just use
It's like
AI.
Linux.
AI will figure it all out. So then
Zephyr's great. Learn the device tree.
yeah, right. In the last month or two, I've come across some interesting new things that have gotten me started on a couple more DS pod boards, and
Okay.
I'll look into those a little bit further. But
Okay.
should I just kind of jump
You can-
into the module here? So this
Sure.
module that I've got is essentially the carrier, and what it is there's a front panel that can be mounted in a standard Eurorack system, and then there's an electronics board that's behind it, and that electronics board has a socket for plugging in the pod, which is just the breakout board for whichever processor you're trying to use. And then it also has the interface electronics on it, the converting the 12 plus minus 12 volt power supply of Eurorack into a 3 point or a 5 volt bus voltage that the pod needs.
Okay.
And then also it provides the buffer amplifiers for the audio input and output and the control voltage inputs, as well as the interfaces to the LCD and the encoder knob. And it's fairly simple. There's not a whole lot going on, but it's just the environment in which all of these things live, and then I can write code that talks to it from all the different environments that I'm using.
Just plug in a different
So
module
the first,
and go.
yeah.
Okay.
So the first module that I actually brought up was the CV1800B one. This is the Milk 5. And so on this board you can see I've got a USB connector off on the right hand side. There's a 3-pin serial debug port that I use for talking to it. The 56-pin QFN package right there, that's the entire SoC right there. And then I've also got down in the lower center there's a little analog multiplexer that'll take 4 channels of analog input and mux it into the one A to D input that the SoC has on it. And then over in the bottom left corner there's the audio codec. That's a Nuvoton NAU 88C22, which is stupid cheap. You can buy those at DigiKey for like $1 a piece.
Nice.
So I did a shootout of that against some of the higher end codecs that I've used in other products that I've done, and it performs pretty well. I was happy with the way it works, so I decided to standardize on that for this project. And then of course the SD card socket, and that holds the entire file system that the little Linux running on the SoC uses. What you don't see is the back of the board is full of the various power supplies, because the SoC needs like 4 different power supplies to run, and so I've got a bunch of little switchers and LDOs on the back for all of that. But, so
the back of the board.
Yeah, on the back of
Okay.
that purple board there.
Okay, so we can't do like board to board directly. You'd have to route out.
Yeah, you have
a
to have
section.
a little clearance. You can't solder it down directly like you would with a castellated board.
Yeah. Okay.
So the interesting aspects of the hardware here are the CV1800B Linux SoC. That's got a 1 gigahertz RISC-V primary CPU in it, but it's also got a 700 megahertz rated secondary CPU, and these things don't access the internal resources the same way. So you can't turn this into a multi-processing system. You can't make a dual core out of it, really. That so that your Linux only can see one core at a time. And their software development kit gives you a free RTOS that's running on that secondary
Okay.
CPU. And in their applications, they use that to manage the image processing pipeline. And they have,
Very cool.
this chip has got an incredible amount of image processing built in it. It's got all of the stuff for, image color correction and geometry correction, and it's even got a little 0.5 tops neural processor in it, so that you can do feature recognition on the images as they come through.
Like object.
And they've
detection.
got demo code for all of that in their development
Basis.
system.
Yeah.
But
Cool.
then you go down a little bit further. What else? Like I say, it's got an audio codec in it, and that I am not using that one because in this package they only bring out one channel, and so it's not enough for everything that I wanted to do. I had to do a fair amount of work to get the device tree to recognize the external I2S port, so that I could hook up an external codec. But once I got that figured out, it all worked out pretty well.
Yeah.
I've got the
Little auto
schematic. Yeah, I've got a schematic of the. This is the entire board right here. So we've got 4 different regulators. We've got the analog mux for the control voltage inputs, the SD card up in this area, and USB. I didn't put any USB protection on this because I didn't expect that it would be something that you would access all the time. But it's fairly easy to use. You can still buy these parts online. They're about you can get like 5 of them for about $20, so they're about $4 a piece. And because it's a little QFN package, it's extremely easy to use. So the main thing is you spend more time on the software than you do on the hardware. And so that's pretty much the software and hardware. And so the question is, how did it work? Once I got in there and I added my my user interface and the audio effects stuff, how well did it work? And
Yeah.
the main thing that I can say about this is that, first of all, since it runs Linux, any kind of high intensity computing that you need to do has to share the load with the operating system. And so my experience in using some of my more heavyweight algorithms, like I've got some effects algorithms that use something called a phase vocoder, which is you do an FFT and then you do a bit of processing and then you do an inverse FFT of that, and you can do some fairly interesting stuff that way that's not possible with simpler things like just basic delays and reverbs and things. So what happens then is it needs a whole lot of compute power to do all those FFTs.
Right.
And my experience was that 1 gigahertz RISC-V processor couldn't perform it as well as a 500 megahertz STM32H7
Interesting.
running almost the exact same algorithm, just because there's so much other overhead going on in the system.
Right.
But it was a fun experiment, and it's nice to have all that power in such a small package.
Yeah.
One of the things that I've seen, that the Milk 5 people have a user community on a website where you can get in and see what everybody's doing. And 2 years ago, it was really busy. There was a lot of people on there. And there were a couple of people who actually went in and did a bare metal system running on top of that SoC.
Okay.
And
That
would
might be
one
better for
thing to
this kind of app. Yeah.
Absolutely, yeah. I mean, you don't need all of the operating system support that is available in Linux for the kind of stuff that I'm doing. And so I think if I ever wanted, if I ever got to a point where I had nothing to do for 6 months, I might play around with trying to do bare metal on one of these things. I know that there's something like that for Raspberry Pi.
Yeah.
There's an operating system called Circle that has all kinds of audio and graphic stuff in it, and it's not running on top of Linux. So
Very cool.
that's always something that would be interesting to do, but there always seems to be more things to do instead.
Yeah. More metal.
Yep, yep. So that's the CD1800B version. Uh, I did an RP2350 version, so here's that one.
Ooh.
Um, so again, we've got the same USB connector. We've got the same codec on it down in the lower left. On this one, the RP2350 has a fairly nice QSPI interface that they use for storing their code in an external flash. And this time around, they added another chip select line, and they added the ability to do writes. So now you can have an external uh, QSPI flash chip on there. And so I threw that on. And so now we've got an RP2350 with 8 megabytes of external RAM.
Nice.
And that's super handy for doing any kinds of long digital delays or sample capture or things like that. And that was the primary thing that I wanted to play around with on here. But also, because the RP2350 has dual cores in it, it's both, you can get either dual core ARM Cortex M33, or they have that crazy homemade RISC-V processor that one of the developers at RPi put together. I forget what that one's called. You probably remember, but I haven't tried those yet. Everything that I've done on the RP2350, I've done with the Cortex M33.
Okay. Yeah, the main core.
Yeah.
Okay.
And so this one worked out pretty well. I was able to get quite a lot of stuff running on it. And the other thing that I found was I've been overclocking it, and I can overclock this RP2350 to like 300 and about 320 megahertz,
Cool.
and it runs just fine.
Wow.
And that's pretty fun to have a dual core system running at 320 megahertz with full floating point and lots of memory on it. So
Yeah.
I've been having a good time playing around with that for the last couple of months.
Does it get warm?
Get an idea. Say what?
Does it get warm?
It. I did not notice it getting warm. I put my
Very
finger
cool.
on it, and it doesn't feel like it's any warmer than anything else on there. So I
Hmm.
think it's in pretty good shape in that regard.
Excellent.
They, in researching this, I see that some people have gotten these things running as fast as 700 or 800 megahertz, but they had to cool them with liquid nitrogen. So
Yeah, that's a little extreme.
yeah, I don't quite have the infrastructure for that. But anyway, I've been very pleased with this chip.
Okay.
This is still that first version that came out, and it's got the problem with the IO drivers.
Hmm.
But I don't need pull downs, so that hasn't caused me any problems. So
Yeah, it's cool to see a
I'm pretty
design
happy
based
with it.
on the RP
Yeah,
2350, the
mhm,
newest, coolest Raspberry microcontroller.
right. So again, the results on this one were there were. I haven't tried doing any of the FFT stuff on it yet. I don't think that I would be able to get it to work because it was barely usable on a 400 megahertz uh, Cortex M7. So I would probably
Yeah.
have to do a little bit more exploration of overclocking on this thing to get the FFT stuff
Since it's
running on it.
M3, right?
This is M33, yeah.
Yeah. Okay.
So,
Not as much
but
horsepower.
there's certainly that's an unexplored area. It might actually work, but I haven't explored it yet. So
Okay.
overall, very happy with it. I I would strongly recommend that people consider using RP2350 for this kind of stuff. The I squared S interface via the PIO block works just fine. Have had no issues with that. So definitely consider it. I think the main problem that I've had with this one, if I had to say anything at all, is just the resolution, the functionality of the on-chip A to D converter.
Hmm.
It does not work very well. You have to run it kind of slowly, and the 12-bit accuracy is not very good. You end up with a lot of noise and jitter in the results. So you're trying to do fast conversions or trying to get accuracy, you probably need to use an external converter.
Yeah. So it's probably like 10-bit ENOB or something like that. 8-bit.
Yeah, I mean, it says that it's. I think if you look in the spec sheet, they say that they guarantee 10-bit accuracy, but I don't know.
Okay.
There's a lot of compromises on there, but I understand.
It's a
Getting a good
microcontroller.
mixed signal implementation is something that takes a lot of experience. Even STM32 chips had crappy A to Ds on them back in the day, and it took them a long time to get those things squared away. So,
Oh, I've had plenty of experience with bad ADCs on microcontrollers. They
yep,
leave you wanting, and you end up with an external SPI usually.
yes.
Yeah.
So that's the RP2350 version. So then the next one is the ESP32S3.
Ooh,
I don't have, oh, there it is. There's the built up picture of it.
nice.
Um, so this one worked out pretty well. I actually have another effects module that I did with an ESP32S3 a couple years ago. So this one I just kind of lifted a lot of the circuitry off of that one and plunked it down here. That one, the previous one, I had done a lot of experiments with touch interfaces using the touch sense capability that's built into it,
Mm-hmm.
but that didn't carry over into this design. So this one's just the same basic LCD and encoder user interface that we had on the others. Um,
Okay.
this one, there's only thing that's unique about this is, of course, since it's an ESP32, is I put on the capability to do, hook up an antenna to it so that you could do any of the Wi-Fi or Bluetooth stuff on it that this chip's capable of.
Yeah, I
And
think it would be pretty neat. You could have like a phone app that kind of replicates the interface or a
absolutely,
web page.
you could definitely expand the amount of control that you have over it through Bluetooth, or you could, use it as some kind of a module that could do streaming, for
Yeah,
instance.
yeah,
And
cool.
I've only explored a very small aspect of that with the Wi-Fi on this thing. So there's definitely a lot of room for exploration on here that I haven't gone into. But as far as the overall application of the thing, I found it very pleasant to use. The ESP IDF that you use for doing all the code development is no big deal. Once you get used to all of the little ways that it works with FreeRTOS sitting there under the hood, and
Yep.
um, the way they use the flash on these things, where they basically set up a bunch of partitions with different things in them. You can use that like non-volatile memory. You can store settings in it, and it's all very nice to use, well thought out. I guess they've moved all the way up to version 6 now. I started out on IDF version 4.4 many years ago,
Yeah.
and they've been making a lot of progress. And as one of the listeners here said, my understanding is that they're moving everything over to the new
Zephyr.
operating system. Yep,
Yeah.
Zephyr, and
Yeah.
that'll
No
be
time
interesting.
like the presidents to learn how to use Zephyr. I know you're not a big Zephyr person, but we have some Zephyr devs in the
Well,
Query
yeah,
Embedded
I know
channel.
that you know, one of our longtime friends from back in the day is a big Zephyr developer at
Hmm.
one of the big tech companies, and you know, he's done a little bit of work on some previous projects that we did. I guess
Hmm.
he did an FPGA driver for the ICE 40
Oh, for the
in
ICE5
Zephyr.
wireless. Yes.
Yeah.
He actually ported
Yeah.
the Zephyr to the main processor with the ESP32, but he also
Uh-huh.
ported it to a soft core that's in the FPGA for some
Cool.
Zephyrception.
Yeah. I don't
Very
know
cool.
enough about Zephyr, but I suspect that I'm going to have to learn. So,
Yeah, right. Yeah, and a new download and
yep.
lots of exploring. You'll
As
find the
soon
way
as
that they
soon
do
as
device tree is very interesting. It's like a
yeah,
code
that's the
generating
thing that
method.
kind of set my teeth on edge was as soon as I saw device tree in there, I started thinking, oh no.
Yep.
The joy of Zephyr is device tree is processed completely by the preprocessor, and it brings in only the code you need so
Mhm.
that your final image is minimal.
Right.
Okay, so it's not looking at the device tree
It's
at boot
not
time.
dynamic.
No,
No.
Excellent,
no,
excellent. That's good to know.
it's
Yeah.
100% processed before compile.
Right.
That's excellent. Yeah.
Generates header files. Does some magic.
Hmm.
Once you see how it works, you're like, this is very clever.
Uh-huh. Well, I guess I need to bite the bullet and get in there and try it out.
Get a Zephyr compatible board. Hey, wait, we designed one.
Yeah. So the results on this one were also encouraging. Had access to a large chunk of memory, which was good to have. Um, the dual core was good because I was running the user interface on one core and running the audio processing on the other. And that's the
Nice.
same thing I did on the RB2350, so that ported over very very similarly. Um, I have not yet explored the vector stuff on the Tensilica cores. That's still something that I'd like to play around with. So
Yeah. A lot of hardware options now. You've gone through what 4 boards now, right?
yeah, yeah, creating a lot of what technical debt, right?
So, yeah. Well, that's the thing. Like, for every one of those, you have a software ecosystem that's slightly different, and you have to kind of shoehorn your app onto the different platforms. Hopefully, it wasn't too bad. It sounds like
So
it
then the
wasn't though.
fourth one that I did, this is with the STM32H7R3.
Nice.
Um, these are weird processors. ST has got some of these high-end processors with big CPU cores in them and lots of RAM,
Hmm.
but they make them with almost no flash memory. And the idea is that you're supposed to have an external SPI or QSPI flash,
Hmm.
and then you can access that. You can either store the code out there and run it and execute in place, and they have a fairly good uh, cache so that you can run that without too much of a penalty. Or you can copy it out of the SPI flash and into the on-chip RAM for stuff that is running really fast. And so I've played around with that. Um, I actually ended up making a port of Tiny UF2, which is a bootloader that's based on the same ideas that the RP2350 of the Raspberry Pi parts use,
Okay.
where you you stick it in to you hook it up to USB, and it looks like it's a mass storage device,
Right.
and
You
you
have to.
just drop a .uf2 file on it, and then the um, little processor on there parses that UF2 file into and loads it into the flash memory, and then reboots into the application as soon as it's done with that.
Yeah.
And it was fairly straightforward to get this working with Tiny UF2. I was really happy with that. Um,
Yeah. Adafruit uses UF2 implementation for Circuit Python.
yeah, I guess the maintainer of the Tiny USB and Tiny UF2 is supported by the folks at Adafruit, and
I wouldn't be surprised because they use it so much.
yeah, and they've got ports to most of the little USB microcontrollers that are out there right now. The reason that it was fairly easy for me to do it on this one was that they already had a port for uh, the H7R series parts, and all I had to do in this case was just a few little tweaks for the way that I had it hooked up on my board. So basically, I just had to create a board support package for this board, and got it all working pretty well. That was fun to do. Um, so yeah, this one's unique in that it's got a 600 megahertz maximum clock, so it runs a little faster than the other STM32s that I've used in the past.
Okay.
And one of the things that's unique on this one that you don't see on other STM32s is that it has a high-speed USB 5 built in,
Nice.
so you can do full 480 megahertz USB on this guy without any kind of extra hardware.
Nice.
And I wanted to play around with that. And I got that working. That was very simple to do. If you'll notice on the renderings that I have here, I've shown both the front and the back of the board.
Yeah.
I actually have little solder blob jumpers that allow me to select which of the two USB ports on the device are brought out to the connector, and so I can use either the full speed port or the high speed port. Now the reason you might want to use the full speed port is that that is the one that's connected to their built-in bootloader. So when you do a reset and hold down that boot button, which is right here on the
You're gonna
board,
want that bootloader.
yeah, you get the factory installed bootloader, which knows how to do device firmware update class USB stuff, and
Yeah.
so that's a really great way to do some initial test and debug on these devices before you
Without your
start getting
software
into
debugger.
but, yep,
Yeah.
yep.
Very cool.
So that is fun to do. But yeah, then once I wrung out that full speed port and proved to myself that that all worked, then I swapped the solder blobs over to the high speed port and got that one working too. And interestingly enough, I didn't see any great difference in performance between the full speed and the high speed port for the tiny UF2 application, of course, because that's limited by the speed of programming the flash. I don't think that the USB is really a
It's like
limiting
a
factor
limiting.
in there.
Yeah, makes sense. Flash is
But,
slow, especially Spy Flash.
Yep.
Spy Noir.
So this worked pretty well. I was able to get my high-powered spectral FFT-based effects running on that without
Nice.
any trouble at all. And of course, the CPU load on this 600 megahertz device was a little bit lower than it was at what I'd seen on some of my others. The performance of running code out of the external flash memory through the QSPI port is not significantly worse. I don't see that really affecting things much, especially if I load the heavy DSP stuff into the on-chip memory. And I had some interesting experiments with doing overlays that I had explored on the RP2350 version, where you create an area in on-chip RAM, and then you can compile a bunch of code that will all map into that area, and then you just copy it in when you need it to, and
Firmware.
it's all done. It's all done with tricks in the linker script, and but it works really well. And all you need is a little bit of interface code to do the copying when you select a new algorithm. And so I did that on the 2350, and
Cool.
I haven't done it on here yet, but I want to try it on this one because
Yeah.
I think
Do you have any kind of
the
like
limited-
too long didn't read kind of documentation on that, or is it kind of still in the out there random websites? Because I know it's probably not as super straightforward.
yeah, it's actually pretty simple once you look at it. But it's one of those things that I'd never really explored before. So,
It's a neat idea.
yep. So let's see. So that's the STM32H7R3.
Very
Um, there's a lot of stuff going on the back of this one. One thing that I might mention. Um, they say that you can put an external PS RAM on that QSPI bus, and then you can do reads and writes to it. And
That'd be cool.
I tried that. I tried that, and I
Mm-hmm.
could not get that to work reliably. Um,
Mm.
I could do it in what they call indirect mode, where you load blocks of code up
Cached.
and DMA them out there as though it were a SPI flash device.
Right.
But when you want to memory map it and read and write to that memory as though it were mapped into your address space, that for some reason I just could not get that to work reliably. It was like it was queuing stuff up, and then if I didn't, you know, meter the accesses to that memory, then it would get confused and drop stuff and start writing zeros into it. And
Ooh.
it
Yeah, sounds
it
like
was
a cache
just,
coherency thing.
yeah, it was a mess. And the thing that's, weird is ESP32 has no trouble with that, and the RP2350 had no trouble with that. So I was really surprised with the fact that the STM32 just didn't seem to be able to do it. Um, it may have been that I had the XSpy port configured incorrectly. Maybe I was holding my mouth wrong, but I did a lot of looking around to see whether I could, if anybody else had gotten it to work. And I didn't see anybody else who was trying to use RAM on that port, and B, you know, never saw anybody mention anything about issues.
Yeah, that
Um,
means you're gonna go to the forums for the chip manufacturer, which
yeah,
can be fun
yeah.
sometimes.
There's do you know of a fellow named Andrew Zonenberg?
Yes.
Um, he works for an outfit that does security analysis
Right.
on hardware and software, and his hobby, he's got a full reverse engineering lab built into his garage,
Mm.
and his hobby is just to tear chips down, but he also likes to build FPGA boards for doing high speed data acquisition.
Yep.
And he was doing an experiment where he took an STM32H7 part, and he was trying to use the OctoSpy port to do to interface to large FPGAs so that he could
Cool.
treat the FPGA like it was an external memory and just
Mm.
load enormous quantities of registers into it over the XSpy port as though they
Cool.
were memory mapped. And he fought against that for a long time, and he came up with this huge write up of all the things that were wrong with the STM32
Oh boy.
Octospy ports, and that's worth reading if you ever want to see some frustration.
Yeah. I could put a link to it if you have one.
Yeah, I'll see if I
In the
can dig
chat.
that up. So
Cool.
anyway, so that was my experience with the H7R3, and that was let's see, that was pretty much the last one that I've actually built up and worked with.
This was
Um,
very recently. I'm assuming. That's a
yeah,
lot
that
of words.
yeah, the H7R3 stuff, I kind of wrapped that up in January.
Okay.
So then a couple weeks ago, ST announced this new series of parts called the U3. So STM32 U3. These are parts that are targeted at the low power market.
Sure.
They've got a single core Cortex M33 running at 96 megahertz max.
Okay.
So that's seems kind of slow,
Right.
but they have one interesting aspect of them, and that is this thing called the HSP. And the HSP is a coprocessor that's living alongside the uh, CPU core in there
Okay.
that is set up to do all kinds of fancy vector processing. It can do, you can give it a vector of, many hundreds of entries long, um, and have it generate, sine waves, or you can have it, give it a chunk of data and tell it to do an FFT, and it'll just do an FFT.
That's amazing.
And yeah, and not only that, but uh, you can give it a list of instructions of operations to perform. So you can say, here, I'm putting this vector in this chunk of your memory. I want you to run this operation on it, and when you get done, run this operation on the result, and when you get done, put the result over here. And so I'm fascinated with the notion that something like this might be able to run those spectral effect processing algorithms that I've been exploring for the last few years. I have no idea what the performance of the HSP is. It may be that it's too slow for me, but if it's, it's something that I need to play around with. And
Cool.
so I've got this little board thrown together. I just got the bare PCBs back from Osh Park yes on Friday, I think. And so and I got a bunch of the rest of the parts from DigiKey yesterday. So sometime this week, I'm going to sit down and put one of these together and see what happens.
Very cool. Yeah, I'd like. It'd be cool to in the like maybe in a future episode doing maybe like a demo. I think a demo would be fun.
Yeah, I need to figure out, as much fun as we've had today trying to get my audio working. Um,
Yeah, we're gonna have StreamYard set up soon. Uh,
yeah,
Robert's
once
gonna.
we get that going, I'd be happy to put something together because I've got, we could hook something up and actually listen to what these different effects sound like. That would be kind of fun to play around with. But
I think it would be a lot
def
of fun.
yep. So that's the U3C5, which is TBD at this point. We haven't actually built that up yet. So the final one is going back to our FPGA roots.
Woo! Yeah.
Yeah.
Ice
Michael and
40.
I worked on the Ice 5 wireless 4 years ago. Man, it doesn't seem like
Really?
that long.
Wow.
Yeah.
Yeah. It's pretty
um,
amazing. Time
so
flies.
this one is the Ice 40 UP5K. This is the same FPGA that we had on the Ice 5 wireless. I've got a USB port on it, and I would use something like Sylvan
Yeah.
Munoz. He's
The
got
NO2, the Nitro bootloader.
it. That's it, the Nitro bootloader, NO2 bootloader, and
Yeah.
I've got I've been able to bring that up on some of my other UP5K projects, so I don't
It's
anticipate any
real
issues
easy.
on this one.
Yeah.
Oh yeah, all you got to do is just set a few settings in a configuration file, and you're off to the
Select the
races.
right pins for your
Yep,
USB.
yep.
Yeah.
You have to be a little careful that you don't put them on, pins that are used for special things like clocks or LED drives. But other than that, you're fine.
Yeah.
Um, so what I've done here is put one of those on the board with a USB connection, and then I've got a 4-channel 12-bit external A to D converter for the control voltages, and I've got an I squared S bus interface to the audio codec,
Very cool.
and I've also got an I squared C bus on this, and up here in the corner, I've got an SI5351 clock generator,
Nice.
and that's routed. The output of that is routed to one of the FPGA's global clock inputs. And the
Okay.
idea there is that I can use that to generate accurate audio sample rate clocks
Master clock.
because
Yeah.
exactly the in order to do USB on this device, you have to have a 16 megahertz clock down here, and it uses the PLL in the FPGA to get that to the 48 megahertz it needs for
Right.
the USB interface.
Yep.
Um, and that is not a good frequency for use with audio.
Nope, you want
So
12 megahertz, 12.288.
that's right. You need 12.288 if you want to get accurate audio sample rates. So there's that audio sample rate. And, the SI5351 is an amazing little piece of kit. You can get just about any frequency out of it that you want. And it's nice and clean, clean enough to do radio interfaces. So
Yeah.
there's all kinds of options, little things that I can do with that. I've also put on this board uh, two memories. I've got a PS RAM and I have a 4 megabyte flash for storing the FPGA configurations, and then the PS RAM for audio buffers or whatever. So um, I have done audio work with these UP5K FPGAs in the past. I built a little Eurorack oscillator that used pulse density modulation to get really high quality audio output without having to use a codec.
Yeah.
In this case, I'm actually using a codec, but the neat thing about that one was that I could run my audio oscillators at 16 megahertz and get super high sample rates, which mean very clean emulation of analog waveforms, which
Very
is
cool.
not something that's easy to do when you're running at lower sample rates. But so I do have some experience with audio in these things, but it'll be interesting to see how well it works with more standard I squared S
Yeah.
codec.
You gotta bolt in
So,
the logic for the I square S controller onto your
yeah,
RISC-V. I'm assuming you're gonna use a RISC-V, maybe a Pico RISC-V or something like that.
yeah, that Pico RB32. Throw that in there and see what I can do. But I'll probably also have some actual hardware algorithms, and not rely on the software to be actually managing the data. But
Right. That makes a
see
lot
how
of
that
sense.
goes.
With an FPGA, you have, if you have resources, I know those
Yes,
aren't going to have a ton of resources. There's not a ton of
right.
arithmetic
Yeah,
in
I mean
the low end
this is
FPGAs.
definitely a constrained system. You've only
Yeah.
got 8 multipliers, and you've only got 5,000 some odd processing tiles in there. But it'll
Yeah.
be interesting to play with. It's something to look forward to.
Yeah.
So that's kind of the full wrap up of all the stuff that's in the DS Pod ecosystem. We've got
It's quite a
a
lot.
bunch of stuff that's working now. We've got a bunch of stuff that's coming down the pipe, and I'll be adding more detail to those uh, directories in the
Okay.
GitHub section as
Do you have
I
like a graph
do
of
the
like kind of
development.
this current status for each one, or is it just kind of you
Yeah,
just go by the documents?
yeah. There you go. Have a little percent complete.
Yeah, like a chart, like what's working, what's not, that kind of
Yeah,
stuff. There's a lot going on, so there's a lot of IP there that people could use. I mean,
right. And
once it's
so that was
proven, of course.
right. That's one thing that we were kind of talking about yesterday is what is there for people to look at. I've shown you the schematics of
Mhm.
these things, but I need to like this the module here. I haven't put the KiCad design for that on GitHub yet, but it's all there and it's ready, and that's really something I want to do. But for the daughter cards, um, the hardware design is all there.
Cool.
Um, if you look, yeah, I've got a hardware subdirectory for all of these guys that have the full KiCad design
Okay.
as it
And
was.
does it host some
So,
firmware sources in there as well?
yeah. So, for instance, um, one of the things that is crucial, for instance, on the CV1800, the thing that you really need to do if you want to do any software for these things under Linux is you have to be using their SDK. And so they have a GitHub for that. Um, and what I've done is I've made a fork of their SDK that has all of my changes in it that include the extra drivers that I wrote for the codec and the device tree changes that I made in order to enable the external I2S bus. And so all of that stuff is referenced here, and you can go, for instance, go to my fork of the SDK. You can see all the stuff that's in there. And
Nice.
I haven't really touched this in a long time.
The hashtag
But,
exact steps. Too long.
Yeah,
to read.
exactly. Right.
Yeah.
Um,
Good. Perfect.
So that SDK is available with all of my modifications for this particular hardware. And then the user space application that runs on top of Linux is also compiled within their example stuff. So I've forked their examples and added my application as one of those. And so in here, looking at the code, you can see the ADC driver. So this is Linux user space code that talks to the A to D driver that's available in their kernel. I've got a codec driver here that talks to the codec over the I2C bus. I did not write a kernel driver for that. I'm just using.
So you didn't set
I'm
up
just
a
using.
PCM, so you can't use also utils.
Right, you can't use ALSA on this thing. It's not that it would be impossible to do, but that was a level that I didn't need to get into when all I needed to hear was just some raw control.
Yeah, you can poke the registers with a
Yep,
I2C.
that's all you need to do.
Yeah. Okay.
Right. So I've got the encoder. I did use the standard Linux input driver for that, and that was very easy to configure in device tree. And so the encoder driver here just sits on top of that and uses it. And for the graphics, this is an interesting thing on the CV1800V. I went ahead and I used the frame buffer, the Linux
FBdev.
frame buffer drive
Okay.
to talk to the LCD. And that frame buffer does some interesting things. What it tries to be smart, and if you go in and you poke a pixel here and there on the display, it will wait a little while before it transmits that change to see if you're going to do anything else, so that it can combine stuff and minimize bus traffic.
Sure.
And if you do one pixel in one corner of the display and then another pixel in the opposite corner of the display, then it will refresh the entire display, even though you only changed two pixels.
Oh boy.
And
yeah, they need to work on it.
and so overall, I'm kind of regretting my decision to use the frame buffer driver for my graphic user interface on this. And I might actually disable that at some point in the future and then allow myself to do actual, straight commands to the ST7789 LCD controller chip in there, because it would be a lot faster. As it is right now, I have to be very careful how I manage the updates to the display if I don't want to choke the system doing updates.
Yeah.
So
It makes
that's
a
something to
generic
watch out
interface,
for.
But slow.
Yeah. So FBdev is definitely something to be careful with.
Yeah. I've messed with it in the past.
Mhm.
It usually has, you have to really watch the framing of your SPI, and I remember, you had to run it as fast as you could go, essentially. Otherwise, you wouldn't get the frame rate that you want out of it.
Yep. It's a nuisance. So anyway, just as an example there, looking at that one, we've got the hardware files, we've got the software files. If you want to go in, let's look at the 2350. We look at the firmware on that guy. This is a directory full of directories, and here I have test code to test all the different low-level devices in the system.
Very nice.
So we've got the ADC. We've also got the full effects processing app. We've got Blinky, which is just, this is the code that I run on when I first built it to make sure everything's working.
Yep.
Here's just a straight I squared S driver just to make sure that that interface works. It doesn't do anything else. It doesn't use the display. It doesn't use the encoder, and so forth. So basically, just low-level tests for all that stuff.
Yeah, test stubs, functional test. Cool. All right. So that pretty much covers like the majority of the material. We probably went a little bit over the hour. Yeah, it's okay. Since the audio mess up or whatever that happened in the beginning, we needed a little extra time. I don't think anybody's complaining. So maybe we can pause for a minute, ask the audience if they have any questions before we close it out, and then we can wrap it up. And there's probably like a 20-second lag before they hear us asking. Something around that. And if I don't see anything on the chat, then we can just call it. Unless Lawrence had some questions.
Oh, I'm pretty impressed with all the work you've done in this. It seems like a lifetime of work.
Couple years. Passion project. So yeah, am I correct assuming that you're like mostly retired, Eric?
Yeah, I am mostly retired. I'm consulting for a local startup and doing about 10 hours a week.
Oh, that's Lawrence. I was talking to Eric. You're both.
Oh,
Are we back?
I'm mostly retired too.
Yeah, there you are.
Are we back?
Yeah.
Okay. So, I guess the Twitch stream is over now.
Yeah, pretty much. Let me go ahead and close it out. It was nice talking, and we'll be back next week with even more fun, exciting open harbor content.
Yeah. Well,
Cool.
fill,
All right, let's close
fill
out
the
some of
time.
these streams. Let's kill these streams.